All right, welcome back to Codex. Today we have Keaton Hamm. Keaton Hamm is an assistant professor at the Department of Mathematics at the University of Texas at Arlington. He studied under Thomas Schlemprecht and N. Shivakumar at Texas A&M, receiving his PhD in 2015. From there, he was a postdoc at Vanderbilt and then Arizona before joining the faculty at UT Arlington last year. Keaton is an expert in a variety of topics at the intersection of data science and harmonic analysis. And today he will speak to us on one such topic, namely column subset selection. All right, thanks, Keaton.
All right, let me know if there's any issue with seeing the slides. Otherwise, thank you very much to the organizers for the invitation, and it's happy to be speaking to friends and the internet at large, I suppose. So this is going to be half like really broad introduction to this subject called column selection, and then half discussion of some very recent work that's been done with a variety of collaborators. And I just want to sort of mention at the beginning, you know, that this idea of column selection and column row matrix factorizations, when I first learned about it, it was brought to me by my friend and postdoc mentor, Akram Aldrubi, a few years ago. And we sort of saw it initially as like almost a curiosity and just kind of an interesting little fact in linear algebra that allowed you to form a decomposition of a matrix from column and row submatrices of it. But you know, now that a few years have passed and I've learned more and explored more and even seen more of what has already been done in this area, it's sort of turned into, you know, I've sort of realized that these ideas really come up pretty frequently in a variety of areas. And I think, you know, these ideas are sort of very intimately related to a lot of other things that people are interested in. And I just want to sort of, tell you a story about what column selection is and how it relates to maybe some things that you think about more frequently, and how it sort of interplays with a lot of different areas of mathematics. So, sorry, having trouble. Okay. So first of all, the who, these are sort of a subset of my collaborators, and most of the results that are new that I'll discuss today are with them. So 3 at UCLA, HanQin Cai and Longxiu Huang, who was at Vanderbilt while I was, and then Deanna Needell, who many of you know, and then Jiaqi Li and Tao Wang from Sun Yat-sen. And of course, obligatory thank you to the NSF and the Army, the sponsors. So let me just jump in and say what the problem is. So this is what's called the column subset selection problem. So you can state it equally well for complex valued matrices, but I'm going to state everything for real valued matrices just for simplicity. So suppose I have a matrix, and I'll probably interchangeably consider this a data matrix coming from some sort of data domain, and fix an integer k. And the goal of the problem is to find the subset of columns, or the column submatrix that I'll call C, that minimizes this following quantity. So let's look at what this objective function is, right? So C dagger is the Moore-Penrose pseudo inverse of C, and so C times its pseudo inverse is the orthogonal projection onto the columns spans, or the column space of C, right? So you're essentially saying, find me the best sort of subspace determined by actual columns of A that sort of captures the most information of the data A, right? So I'm projecting all the columns of A onto that subspace, and I want to find the best one. Now, just a few comments on this problem. It's common to replace the spectral norm here with the Frobenius norm. You can state it for any Schotten P norm. That would be the sort of next most common class to consider this. It doesn't change the flavor of things a whole lot. Some of the literature focuses on Frobenius norm just because it's a little easier to analyze sometimes, but I'll probably mostly stick with the spectral norm. Also, the reason for this representation here, taking C times its pseudo inverse, comes from the fact that if I just want to find the if I fix a column submatrix C and I want to find the best representation of A in terms of those columns, so I want to represent A as C times X, then what I have here, this pseudo inverse of C times A, is a solution to this minimization problem in any Schotten-P norm. So the best I can hope to do is actually to just project the columns of A onto the span of the chosen columns orthogonally. Okay, so this is sort of the reason why I state the problem as it is at the top. Okay. Of course, you might suspect when you see this problem is NP hard, and the naive solution is completely intractable, which is to search over all n choose k column submatrices and see which one minimizes the objective function. Okay, so you don't want to do this. I'm not going to talk explicitly about all the ways to sort of approximate solutions to the CSSP, but I'll give you some pointers to how things are done. By the way, let me just say, please, feel free to interject questions and such as I go. And I'm going to be pretty high level at the beginning just to give you the flavor. But if you want me to go into more detail on a point, just let me know. Okay, so why would I do this? Well, there's several reasons. One that I'll talk about more as we go is that this provides interpretable representation of the data, as opposed to representing it in some sort of abstract basis coming from, for instance, the SVD or something like this. So I'll bear that out in a moment. It's used in machine learning for kernel matrix approximation. So many applications in machine learning require you to compute a very large kernel matrix, and you can do it approximately by sort of only computing a few columns and rows of your kernel matrix and approximating the whole kernel matrix that way rather than computing the entire thing. The two that will be more the focus of this talk are these ideas here. This can provide you a fast and relatively good approximation to the SVD in a certain sense. Fast meaning it's computationally much cheaper than computing the SVD. And it can give you sort of robust low rank matrix approximations. And then the last one I just mentioned because there was a talk in this codex series a few weeks ago by Karen Schnoss that was very interesting. And she was discussing sort of randomly sampling elements of a dictionary. And so these ideas are related to each other, and there's some back and forth that could be done in that area. Some sample applications where this occurs. This idea can be used to solve the subspace clustering problem, where you have data coming from a union of subspaces and you want to cluster it according to which data is in which subspace. It also has applications in computer vision, such as motion segmentation or facial recognition. Some of those are tied into subspace clustering, but this idea also has application to those areas without appealing to subspace clustering. It's a method of sort of quickly sketching massive data matrices. And there's a whole industry of this. And in some sense, some of these ideas of column subset selection and projection are sort of a specialized subcase of some of the random projection ideas of the Halko-Martensen-Trop paper, if you're familiar with this. It's useful in image processing. I'll give you some examples of that later. And then people have used it for NLP. Actually, it's been applied to a much wider variety of things, including astronomy and many other areas. So I want to just give you, here are some like key themes if you ever start to look into column selection. here are just sort of a few takeaways that I've gained over the years of sort of delving into this. And a lot of these will be highlighted a bit later. So the first key theme is something that we're all familiar with from our signal processing background. Oversampling columns can be your friend, and it gives you good approximations, very good approximations to the truncated SVD. And I'll make this a bit more precise later, but if I'll have some oversampling factor P, and if I sample P times K columns, I can approximate the truncated SVD of order K. These techniques work really well for approximately low rank matrices. If you have a truly full rank matrix that has sort of no obvious spectral gap or something like this, this is probably not the technique for you, so it's not applicable everywhere. Random sampling of columns can be very effective in a variety of circumstances, and there are also some nice sort of hybrid random and plus deterministic column sampling methods that can achieve some really good results. And then the last theme is one of the selling points of using these types of representations of your data is for interpretability. So let me delve into what I mean by that a little bit. Okay, so I'm going to sort of steal an example from this paper by Mahoney and Drinius from the National Proceedings of the National Academy in 2009. So let's suppose I'm a physician or a researcher or something, and I have a data matrix where I have a collection of patients, and for each patient I collect data that I'll call features. So this could be sort of a time series of different biomarkers, or it could be gene expression levels, something like that. So let's say, for example, that the features are different gene expression levels. And ultimately, I might want to do a variety of things with this data. I could try to do some sort of community detection where I sort of try to figure out groups within my patients that are similar to each other and then look at their genetic markers. Or I could do that on the gene side and try to group genes together in some natural way to try to find which ones are sort of contributing to a certain disease that I want to understand. And if you think about what happens, like let's suppose I just do the first thing that I would think of on this matrix, and that's PCA. I center the data, I compute the SVD, and then this sort of gives me, in some sense, the best representation of my data. The problem with that is that the singular vectors are linear combinations of the features, let's say, if I'm looking at the left singular vectors, right? And so what I might find is I have some sort of strange linear combination of these features, of these genetic markers, that is according to PCA meaningful, or it sort of finds the direction of most variance within my set of patients. If I want to draw a direct conclusion from that, it's difficult, and the reason is because I did this sort of I'm now looking at things in this abstract basis coming from PCA. On the other hand, if I factorize my matrix as a product of actual columns of it, so in this case, patients, times some coefficient matrix X, what I now have is, if I get in a new patient, I represent it in terms of a subset of the rest of them. Or if I do this by taking transposes, I look at a new gene expression and I sort of can represent it through as a combination of the other genes. And the reason I say interpretability here, or this is an interpretable representation, is that I actually know in this case what the basis vectors are because they're a given gene or a given patient, depending on how I do this, okay? And so if you're doing sort of an actual domain science application, this could be very important so that you don't come to spurious conclusions. Here's a nice example also that just illustrates this fact and sort of some of the differences from PCA. This is by in a paper by Sorensen and Ombre from 2016. So you have a mixture of two Gaussians here, and the red vectors on the left are the principal components that you get from PCA. And if you stop and think about this for a moment, this is what you kind of should expect, because PCA is just finding the direction of largest variance within the whole data set. And so what ends up happening is essentially PCA is treating this data set really as this sort of enlarged Gaussian distribution, as opposed to finding really that it's these two different ones, right? On the right, what you have are actually columns of the matrix given by C times its pseudo inverse that you would get from doing column selection. And this is done by taking your data, considering it as a 2 by n matrix, choose some small number of columns. You could choose n divided by 4, n divided by 2, something, anything like that, and you'll get this result. And these are the column vectors you get. And you see that it's telling you more or less the largest variance of each Gaussian distribution. So there's something kind of interesting and non-trivial going on here that gives you a different sort of view of the data than PCA, precisely because you're constraining to looking within the data itself. Okay, just as a sample application of this idea, I won't dwell on this too much, but here's sort of a meta theorem that I state imprecisely. So suppose I have columns drawn from a union of subspaces, and then under some somewhat idealized assumptions on the subspaces, if I find a representation like this, such as the one I mentioned before, then I can cluster the data according to subspaces, meaning that I can find an assignment function that tells me which subspace a given column is in. So these references all give variations on this. The first two are based on sort of some sparse minimization problems that are sort of naturally similar to compressed sensing. And the last two are done direct, they find this directly from a matrix factorization. Okay, and the takeaway is in this setting, so you can also do this by the SVD, but the algorithms in these works are faster and actually more robust to noise. Okay, so I won't go too deeply into this, but I want to tell you what are some of the ways that people actually select these columns. So the first sort of random sampling variant is that I come up with a probability distribution over the columns, and then I sample from it, you know, with or without replacement, kind of as you like. Okay, so there are three, the most common distributions are the following ones. So the easiest, of course, is just the uniform distribution. So I'm equally likely to select each column. The second one is according to column length. So the Frobenius norm in the denominator is just a normalization to make it a probability measure. But essentially, you choose column I with probability proportional to the Euclidean length of the column. So you prioritize large columns and deprioritize small magnitude columns. And then leverage scores, which have sort of a rank estimation parameter K in them. These are essentially row norms of truncated singular vectors of your matrix. So V sub K are the first K columns of the right singular vectors of your data matrix, and you're looking at the length of the row norms there. And so I'll talk a little bit more about it later, but these distributions, the amount of information you use about the matrix increases as you go down, and the computational complexity also increases as you go down the list. And error guarantees essentially go the opposite. Leverage scores are in some sense the optimal distribution to choose from, even though they're the most expensive. Okay, and each one has pros and cons. For instance, column length, I could have a lot of linearly dependent columns that are large, and then a few linearly independent columns that are important but have small magnitude, and sampling by column length could be really bad in this instance. Some initial works in this area use Bernoulli trials on each column. Those typically were done by the Bernoulli probability, success probability being related to the column length. The only caveat in doing this is, well, two caveats. One, the error guarantees are not as good as state of the art anymore. They have the error guarantees sort of have the norm of the matrix A in them, and this is undesirable. And also, just as a note, if you do this, it does require rescaling the columns when you go to do a reconstruction. A couple of deterministic sampling methods. One is DEIM, or discrete empirical interpolation method. This was originally introduced by Gu and Eisenstadt, and then in the CUR context by Sorensen and Ombre, which I already mentioned. And there is a greedy column selection algorithm by Avron and Boutsidis that does work fairly well. Again, both of these require computing the SVD, as does computing leverage scores. So there's always some trade-offs here. So for all of these column selection schemes, how should we measure the quality? Well, so first, remember everybody's favorite linear algebra theorem, the Eckart-Young-Mirsky theorem. Okay, maybe that's a bold statement. But if I take a column, if I take k columns of a matrix, then I have a lower bound on this projection given by the error incurred by taking the truncated SVD of order k. And so what we're gonna ask for is, so I wanna find some sort of small oversampling factor, possibly depending on some epsilon, that when I choose, slightly more columns than k, I get an upper bound of something on the order of 1 plus epsilon times the SVD error. So basically, I want to get a few more columns. I want to allow myself that flexibility, but I want to well approximate sort of within a tight range the truncated SVD error. Okay. And so that there's just one comment here. I do have to oversample in sort of a typical case to guarantee something like this. I can have sort of arbitrarily bad adversarial matrices where this can sort of be arbitrarily larger than the truncated SVD error. So I essentially mentioned this before. Computational complexity leverage scores are the largest, going down to uniform being obviously the cheapest because it's constant time. The guarantees go essentially in that order. So leverage scores give the best guarantee with the best oversampling, like the smallest oversampling factor. Column length and uniform sampling typically give worse guarantees. In fact, at the moment for spectral norm, I believe there is no order 1 plus epsilon guarantee for either column length or uniform sampling. Those actually look like the SVD error plus epsilon times the norm of A. So those are a bit worse. And yeah, like I say, less oversampling with leverage, and it goes up from there. There is one exception to this, and this is a takeaway from all of this, and I'll exploit this later on. If A has incoherent columns, uniform sampling works very well. This is for CUR decompositions. This is in a paper by Chu and Demonet, but this idea was around before then, sort of from other works.
Keaton, when you say incoherent here, do you mean that the columns are incoherent with each other, or they're all incoherent with the identity basis?
I mean, so it has, well, I'll define it later, but if I look at the singular vectors, the rows of the truncated singular vectors, it's at most square root of some mu r over n, and mu is significantly smaller than n over r.
Thank you.
Yep. So there are many other theorems and many other sampling methods that I won't mention. Here's just a taste of some of the things you can do. So this is a bit older theorem by Mahoney and Drinius. If I sample according to leverage scores, I can get away with only sampling k log k divided by epsilon squared columns, and I get a very nice factor here, 1 plus epsilon over 2. The only one mild caveat here is this is a Frobenius norm error. It's a bit harder to get spectral norm bounds in this case. So k log k is a really mild oversampling factor. The 1 over epsilon squared, I think there are some that may have smaller epsilon dependence, and it's definitely not known if this is optimal, I don't think, but that it's, compared to some of the other bounds, it's relatively mild. There are some that are, you know, epsilon to the 8th or something like this. Okay, so I want to switch gears and move on to talking about these notions to find either low-rank decompositions or low-rank approximations to arbitrary matrices. So we've talked already about sort of factorizing a matrix as columns times x. These are typically called interpolative decompositions. This paper by Verona and Martinson is sort of a canonical one in that area. What I didn't talk about is that if we're being ambitious, if I'm asking to subsample columns, I might as well also ask to subsample rows. And now I can look at factorizations of my matrix where I have column submatrix on the left and row submatrix on the right, and then something to sort of mix the two in between. These are typically called CUR decompositions. I will say later on what natural choices are for you. Just so that you're aware, these go by many names, so cross approximation and pseudo-skeleton decompositions from the Russian linear algebra community. And then in the special case where A is a kernel matrix or generally a symmetric positive semi-definite matrix, this is called the Nyström method, in which case you use the same rows as columns so that your approximation is symmetric. So there are two natural choices for you in the CUR decomposition. One is this sort of funky thing where I take the pseudo inverses of C and R on the right and then A in the middle. I'll explain why in a second. And the other is to just take the intersection of the column and row submatrices and take pseudo inverses. Okay, so let's start with the second one. So I'll take my column C, that's the red columns here, and then R are the blue rows here, and then U is this purple matrix that in this case is 3 by 4. And the theorem, which, so Longxiu and I trace it back at least implicitly to Penrose's follow-up paper on the pseudo inverse that bears his name. It goes back at least that far, at least in some guys. I'm not sure exactly how far back it goes, but the theorem is that if the rank of U, that very small submatrix, is the same as the rank of A, then I get this exact factorization where A is column times the pseudo inverse of U times R. Okay. So again, so obviously this is requiring that A is essentially low rank, and I'm choosing enough columns and rows. Okay, so the other one is sort of more inspired by the column subset selection problem, and that's that, you know, while I'm projecting on the left onto the span of those columns, I might as well project on the right onto the span of the rows. And this also comes from this observation that if I fix C and R, then the solution to this, or a solution to this minimization problem, is given by this matrix that I put earlier. This is true in the Frobenius norm. Just beware, it is not true in the spectral norm. And I'm not sure about the rest of the Schotten-P norms. My guess is that it's most likely not true for all of them. Okay. So those are two natural choices. And some time ago, Longxiu and I found the following characterization, and that is essentially, so all the notation is as before. Now U I'm going to fix to be the intersection of C and R as it was in the first case. And the following things are equivalent. So the folklore theorem was 1 implied 2, as I showed you before. It turns out those are equivalent and equivalent to A being equal to this projection-based decomposition. Some of the more interesting ones so if you're careful, you'll remember that pseudo inverses don't act like inverses in this way. So it's not obvious that 2 and 4 should be equivalent, and in general they're not, but in this case they happen to be. And then part 5 is that I only need to check the rank on the columns and rows independently, and if those match, then I get a decomposition. This allows you to prove some things and improve some of the original bounds on CUR decompositions by doing the column and row selection independently from each other. Some of the initial bounds would be essentially trying to enforce this condition, and they would choose columns first, followed by rows, and you end up having to sort of actually oversample rows a little bit, and you don't have to do that because of this. And I'll kind of skip the sure decomposition one, but this is actually 6 is actually most in line with what's in the Penrose paper from a long time ago. Oh, by the way, I will mention at this point, if I have time at the end, I will discuss a very recent extension of this to tensors and tensor CUR type decompositions. If I don't get to it and you're interested, feel free to log that away and ask me a question at the end. So now I want to talk about some recent results. And basically what I want to get across is it turns out you can use CUR decompositions in a couple of sort of complementary ways in the Robust PCA framework to do low rank approximation. So the Robust PCA framework is, I'm going to assume that I observe a data matrix, which is an actually low rank matrix L, and L will have rank R, plus a sparse noise matrix. And so S has few non-zero entries, but they can be of arbitrary magnitude. And my goal is to return an estimate of L. But I'm going to focus on the simplest case. I could add a small noise perturbation here, and the analysis will go through in some sense, but I'm just going to worry about the low rank plus sparse model. Okay, so I'm going to make 2 assumptions as are common in Robust PCA. One is that the low rank part has good incoherence. So if I look at the compact SVD, I'm looking at row norms of the left and right singular vectors, and I can compute these quantities mu1 and mu2, which are the column and row incoherences respectively, and I want them to be small compared to m over r. So I essentially want them to be sort of constant with respect to m or n. And then I'll assume the matrix S is alpha sparse, so it has at most alpha n or alpha m non-zero entries along its rows and columns respectively. Okay.
Sorry, real quick, just to make sure it's clear. By compact SVD, you mean you've changed that sigma to an L by L diagonal matrix, and then you've truncated appropriately the W and the V so that it multiplies out to be that rank in L approximation.
Correct, yeah, so okay. L is m by r, sigma is r by r, V transpose is r by n, that's correct. Yeah, thanks. So here's sort of just a proto algorithm that we decided to look at just to kind of see, in a sense, what came of this. And that is, so I'm going to assume, again, the things I said before. And then for the moment, our PCA is going to be your favorite Robust PCA algorithm, whatever you like. Okay. And my goal is to output an approximation to the low rank part. And we're just going to do something very simple. So what I'm going to do is I'm first going to draw indices, row and column indices uniformly at random. And then I'm going to set what I'll call C tilde and R tilde to be column and row submatrices of the noisy data. And then, so if my matrix is huge, doing robust PCA on the entire matrix could be fairly costly. So what I'm trying to do is leverage this idea of column and row sampling to make my life easier computationally. So what I'll do is I'll perform robust PCA with my target rank parameter R on both the column and row submatrix of the noisy observations. And that will return me, that will return me estimates of column and submatrices of L. So C hat here should be the column submatrix of L, and R hat should be the row submatrix of L according to those indices. And then I get also the column and row submatrices of the sparse noise S. And then I'm going to return a CUR decomposition or CUR approximation of L by using the version where I take now, so C hat I here should be L hat IJ, right? So this is the case where I take the intersection. Okay, so just remember, so typically like robust PCA, obviously the goal is to give a low rank approximation of L, but you do it typically by returning an approximation to the SVD. So you return, the approximation of the singular vectors and singular values. So this is sort of doing something different in that it's returning to you a CUR decomposition as opposed to an SVD. But it's also, you're trying to leverage this idea of sampling rows and columns to give you a bit less computational cost. So now's a good time for a small amount of audience participation. What do I need for this algorithm to actually function or to work well? Anybody?
I mean, everything in that input line, you need A, you need to know the hyperparameter R, you need a RPCA solver, you need a pseudo random number generator to select I and J.
Right, okay. But basically for the guts of it here, what I need, so keep in mind, I'm trying to run my RPCA algorithm on a submatrix of A, right? So typically, if I'm gonna run robust PCA on the entire matrix, I enforce these incoherence and sparsity assumptions on all of L and all of S, right? So now if I want to apply robust PCA successfully on submatrices of A, I need that the submatrices of L have good incoherence and the submatrices of S have good sparsity, okay? So that's what I need to understand. And this was like, in some sense, a little game, to see like, okay, well, what can we prove about how these properties pass to submatrices based on how I sample columns and rows. So I'm running a little short on time, so I want to speed up a little bit. But here's one of the results here. This has no reference to how I sample columns, but essentially what this theorem says is if I make those assumptions on L, so L has a certain incoherence, S has this has no reference to sparsity. So L has a certain incoherence, then this quantity that we call beta tells you essentially everything that you need to know about how those properties are inherited by the column submatrix C. So beta is, first of all, the first term is the proportion of columns that you choose. And the second, so this is a row submatrix of the truncated or the compact, sorry, right singular vectors, right? So V sub L is a tall thin matrix, and I'm taking a few columns of it, and I'm looking at the norm of its pseudo inverse. And so this is a bit like kind of a key theme in all of this is understanding norms of pseudo inverses of row submatrices of singular vectors will tell you a lot of information about any column selection scheme. The hard part is actually understanding what this norm is, okay? So in this case, basically this quantity beta governs everything. So the nice thing is, and this is expected, column incoherence doesn't change, or at least doesn't get worse, because I'm just choosing a few subcolumns. The row incoherence can inflate, and how it inflates, so all these bounds basically just can be summed up in this. The row incoherence can inflate by this quantity, which is beta squared, so that norm squared times the condition number of L squared. And I throw this third bound in because some robust PCA algorithms will require an estimate on the condition number. If you want to know how the condition number changes, this is sort of an easy bound that you can give. But not all of them require that. Sparsity, maybe I'll just say this really quickly in words. If I sample R log n columns up to some constant factor that depends a little bit on the sparsity parameter, then with high probability that column submatrix of S is 2 alpha sparse if S was alpha sparse. So that part is actually relatively easy. So comments here, the column incoherence is the same no matter how I choose the columns, but then the row incoherence will depend on how I chose the columns. And it's kind of non-trivial in general to estimate norms of those pseudo inverses. Okay, but I will show you some examples where you can say something. So here's one basically if I do maximum volume sampling, so I choose the row submatrix of V that gives me the largest volume, and by volume I mean the product of the singular values, then there's this bound on beta, which is a little hard to parse, but let me just mention for you. If I choose the smallest number of columns I have to choose to hit the rank constraint is R. So if I choose L as R, then beta is order R. Or if I choose all of the columns, which I shouldn't do, but if I do that, then beta is 1, because then I have all the singular vectors, so that quantity is the identity. And the bound on beta is decreasing as L goes from R to N.
Keaton, is it possible to find J?
Yes, that's the problem. You cannot.
Oh, okay.
Yeah, no. There are some approximation algorithms, but for those algorithms, there's no bound on this quantity. Yeah, so that's the problem. The greedy algorithm that I mentioned before is nice. You can choose R columns and you get beta at most R, but it has a non-trivial computational complexity here. It's not horrible, but it does essentially require that you compute the SVD, which we would like to avoid. So now I want to mention this is sort of the least complex sampling scheme I can do is just to sample uniformly, right? And here's a sample theorem. There's a more complicated statement, but this is by choosing some parameters. So basically, if I sample essentially R log R times N columns up to this factor of the incoherence of L uniformly without replacement, then I get beta is a constant, it's bounded by 10. And then let me just skip down to here. The row incoherence of C is no worse than 100 times the condition number squared times the row incoherence of L. And this is with probability at least 1 minus 1 over N. You can play with how you sample here and get different probabilities and smaller bounds, but but this is just sort of a taste of what you can say. So, I mean, you should think here in the regime where n is massive. And in that case, this is not really a big deal. Okay.
Keaton, what sort of techniques are in the proof of this theorem?
Yeah, okay, so, yeah, I have that on the slide to answer your question. It's essentially, so the first ingredient is the theorem I showed before, where beta is the thing that governs everything. And actually, the second is it's essentially an immediate corollary from this theorem of Trop, so this is related to one that was mentioned by Karen Schnaas. It's just a slightly different conclusion. Basically, for incoherent matrices, so there's this sampling factor here, and gamma is some quantity that I can play with, and I'm modifying his statement to have beta, but beta is bounded by this with this probability for all delta. So the theorem statement I put before was choosing delta to be something like 0.99 and getting this to be something like 1 minus 1 over n is what requires gamma to be log of n, essentially. So you can play with that depending on what you want this bound to be. So you could do something like r log r, but then this bound is going to be like 1 minus inverse polynomial in r instead of n. So it kind of depends on what you want there. But yeah, I mean, the main driving force is this theorem, and I will agree with Karen that this is a sort of a secret sauce that makes a lot of things work really well. Okay. And I will skip this. Actually, the upshot is if you want a bound, if you want to put all these pieces together and choose a specific robust PCA algorithm, you can, and it will tell you how much you need to sample, and you can get error bounds of the fault, like relative error bounds like this that say with reasonable probability, I have a relative error bounded by epsilon times the inverse condition number of L. So you can get nice relative error bounds. The computational complexity is not huge. We used the alternating projection robust PCA algorithm. Again, there's a lot of stuff there, so I don't want to. I want to move on to some pictures here. So here's an interesting application, and we're still sort of like understanding this to some extent. What you're seeing is we did foreground background separation on the right. So this is our PCA, and this is what I'll call our CUR, so robust CUR. And so these are only from backgrounds of certain frames of a video sequence. And what you see here actually are these are singular vectors. So first and second singular vectors of the background that we extracted from the robust PCA procedure. And here, what we did was we did a hybrid. So we first did this that proto algorithm that I showed you, where we did robust PCA on selected column and row submatrices, and then we actually did a deterministic column sampling procedure to get down to 2 single columns, which in this case means 2 frames of my video. And here's what you should notice. So remember, again, this is under the guise of interpretability. So on the right, if I'm looking at singular vectors, so first of all, the second singular vectors for the last 2 sequences are essentially meaningless. Here, so this is a restaurant scene, and the background has essentially 2 states, one where the light is coming through the window and one where it's not. And so the singular vectors pick up the most of the background with the light there. And then the second singular value is essentially showing you sometimes you need to negate that light if it's occluded, okay? So, I mean, you can interpret this in terms of what's going on, but still this is sort of, I think you'll agree, this is is kind of a strange thing, a strange image that doesn't really correspond to much. So on the left, here, my claim to you is this. Like I said, there are two canonical states of the background, one with light coming through the window, one with light occluded from the window. And this robust CUR decomposition gives you two frames from the background, one of which captures each state of that video. So the claim is that somehow this column selection procedure can give you like canonical frames within your video. Now, we would like to push this a bit farther, and sort of what I really imagine is what I'd love to have is like a day-night sequence. So if anybody has like a long video or a camera that they can sit out somewhere and film for like 12 hours, let me know. And what I would conjecture is that if you have such a video, you do the background extraction and you run this column selection procedure, you should get two frames, background in day, background at night. Okay, so that's kind of the interesting thing here, is that somehow this is giving you like canonical background frames. Okay, but there's more to explore there. Maybe let me take one more minute if that's okay. This is a different algorithm, and this is a different set of authors, and this recently appeared in Signal Processing Letters. Please don't read this algorithm at the moment, but just basically the upshot is within an iterative robust PCA framework, often I do a sparse update and a low rank update. So I update S and then I update L based on that. Typically the low rank update is an SVD. And all this algorithm says is instead of that, I do CUR. And then my iterative update is a CUR approximation to L instead of an SVD approximation to L. The nice thing is you don't actually have to compute this algorithmically. And so what you're doing here is within your iterations, you're not ever doing the SVD, you're only doing CUR. And again, this is within the iterative robust PCA framework as opposed to externally like the previous version was. And the upshot here is it's screaming fast. So on the complexity end, we can reduce the per iteration cost from n squared to n log squared n up to paying this r squared factor. And you sort of see that linear, this is just an experiment on synthetic data, a time versus dimension to show you that that's sort of happening. And we compared it to accelerating alternating projection and a gradient descent based RPCA solver, and it's lightning fast compared to those, and you can get really good error in really low amount of time. So from an algorithmic standpoint, this is nice because it says I'm just using CUR as a proxy for the SVD, and it's super fast. And if you want, here's just a qualitative, here's the original foreground background image. And I think these are the SVD approximations and these are the CUR approximations. The upshot is there's not really much of a difference, but the time is order of magnitude faster than the other methods. So some future directions, we don't have convergence guarantees for that last method. And we're looking at tensor CUR decompositions, and we'd love to see if we can use this for matrix completion. So that's it. Thank you.
All right. Thanks so much, Keaton. All right. In this COVID world, we don't clap out loud, we press the reaction button. And I'm definitely going to do that. And I think the recording has